Hello, pre-calculus students. Today we're going to go over using some trig identities to rewrite trigonometric expressions. We're going to take ones that look really difficult and turn them into something a little bit simpler. As this example. In our current book on page 351, there's a checkpoint problem at the bottom, and it says, let's take this ugly thing and rewrite it. Try to simplify it. Well, if you look on in this section of the book, 5.1, you'll see there are a lot of trig identities that we could use. We know the reciprocal identities, for instance, that sine and cosecant are reciprocals. We know the Pythagorean identity, sine squared theta plus cosine squared theta equals 1, and it's two related identities. We know that, what else do we know? Oh, we know that tangent theta is sine theta over cosine theta. So there are a bunch of things that we can use to simplify some of these expressions. This is going to require you to use your algebra. Now comes the fun part. Now we're combining trigonometry with algebra. Doesn't get much better than this. So here's our ugly expression. And we'll learn in the next section of some rules and steps to follow, but I noticed that cosecant is 1 over sine, and cosine squared theta can be written in terms of sine. So I thought, let's just put everything in terms of sine. So I rewrote cosine squared theta, substituting in the Pythagorean identity. Took the reciprocal identity and the reciprocal identity. Well, now they both fractions have a sine x in the denominator. So I can combine the numerators. And these two ones cancel out. So this expression here, everywhere it is defined, in other words, everywhere cosecant x is not undefined, this whole expression is equal to negative sine x. Let's take a look at another one. I told you that there was the Pythagorean identity. And there were two others that you can get from this. I'm going to divide everything by sine squared x. And when I do that, I get 1 plus cotangent squared x equals cosecant squared x. So this is another way of writing the Pythagorean identity. And if we had divided everything instead of sine squared, if we had divided everything by cosine squared x, we would get tangent squared x plus cosine squared over cosine squared is 1 equals secant squared x. So now we have three ways of looking at the Pythagorean identity: the black way, the red way, and this green way. It is vitally important that you know how to factor. And if you did not spend enough time factoring in your previous classes, then you have some work to do. And I would recommend memorizing these. These should look familiar even if you haven't memorized them. If you have never done the cubes before, notice if it's a cubed minus b cubed, a minus b is a factor. If it's a cubed plus b cubed, a plus b is a factor. And then notice all the other terms are a squared, ab, and b squared. And there's only one minus in each factoring. So if the minus is here, all of these got to be pluses. And if it's a plus here, it's the AB that's negative. Memorize. If, however, you cannot memorize, you can do some polynomial long division. So let's just do a cubed minus b cubed with coefficients of 0. This is just a cubed minus b cubed. And let's divide it by a minus b. So a goes into a cubed, a squared times, that's a cubed minus a squared b. And I subtract that, a cubed minus a cubed, this first term must always cancel or you've done something wrong. Then 0 minus a negative, that's going to be a positive, a squared b. We'll bring this term down. Now, a goes into a squared b. AB times. A times AB is a squared b. AB times negative b is negative AB squared. And we subtract. Again, that first term cancels. 0 minus a negative is going to be a positive AB squared minus a b cubed. A goes into here. B squared times. That gives me AB squared minus b cubed. So sure enough, a cubed minus b cubed divided by this gives us this, or this times this equals this. Right, another way of factoring is Viatas method. Now, some of you like to do this method and try to. That might be good for Algebra 1. That's not going to serve you well later. So I'm going to show you an algorithm that I use. This -5 will go here, and then 6 times -4 will go here. So this, if this is ax squared plus bx plus c, this down here is ac, this up here is b. Now, if there are two notice this is multiplied. So if there are two numbers that multiply to give -24 and add to give -5, then it is factorable. If there are not two whole numbers that multiply to give 24 and add to give, or at least integers, that multiply to give -24 and add to give -5, then it is not factorable. So I'm looking here and I see -8 and 3. So what I do now, and this is called Viatas method. I'm going to rewrite that -5x as -8x plus 3x. You'll notice all I've done is rewrite this polynomial here. Then I'm going to factor by grouping. I'm going to take out the greatest common factor here. And the greatest common factor here is 1. Now the greatest common factor in these two terms is 3x minus 4, which takes us right back to where we started. So you can see that Viatas method worked for us here, and it will work every time. Now we're going to take the x's out and replace them with trig functions. So now we have cosecant squared, cosecant, and a constant. if it helps you to think of cosecant theta as x, then you can rewrite this as 2x squared minus 7x plus 6, and then factor it. The negative 7 goes here because that's our b value. 2 times 6 is 12. That's our a times c value. I need two numbers that multiply to give 12, add to give negative 7, and those are negative 3 and negative 4. So I rewrite the negative 7x as negative 3x and negative 4x, and factor by grouping. Group the first two, take out the greatest common factor. Group the second two, take out the greatest common factor, making sure that I have the same thing left in the parentheses. If I took out a positive 2 here, that would be negative 2x plus 3, and then you couldn't factor this out. So again, if these two numbers exist, subject to our rules, then this will be factorable, and you will be able to factor something out of both and get the same expression left in these two sets of parentheses. Then you can take the 2x minus 3 out and factor it this way. And then remember, this wasn't an x problem, this was a cosecant theta problem. So now we just substitute cosecant theta in for x. And now I have factored this expression. Let's see if we can simplify this expression. When you see something like this, maybe we want to try a common denominator. So I'm going to multiply this one by 1 minus sine theta over 1 minus sine theta. You know that's legal because this is 1. So I'm going to multiply this one by 1 plus sine theta over 1 plus sine theta. So this gives me 1 minus sine theta over, now this is a plus b times a minus b. That's a squared minus b squared. So that's 1 squared minus sine squared theta, or 1 minus sine squared theta. Now you'll notice that I flew through that. I'm expecting that you know that by now. If you don't, you have work to do. Memorize those factoring rules I gave you. Now this will be 1 plus sine theta all over 1 minus sine squared theta. Oops, there should be an equals here. And now an equals here. So this will be 1 minus sine theta plus 1 plus sine theta all over 1 minus sine squared theta. Now the sine thetas will cancel, so I have 2 over, now 1 minus sine squared theta is cosine squared theta from the Pythagorean identity. So we started with this expression and we ended it here. Now you try. See if you can simplify that. Pause the video, come back when you're done because I'm putting the answer up. Now this is an a squared minus b squared here, so you know you can factor that to a plus b times a minus b. These two terms cancel. You can think of it as if that makes it easier to see that these cancel. So this entire expression simplifies to 1 plus sine theta. Like I said, we're combining trigonometry and algebra now. And why wouldn't you want to, right? So again, I started with an expression, factored it. So let's see, you notice that you could factor a 2 out of here. I didn't notice that when I wrote it, so that would be 2 times x minus 1 times 3x plus 4. And you see down at the end, I get 2 times x minus 1 times 3x plus 4. So anyway, you can see I started here, multiplied it, factored, and got right back to where I started using Viatas method. So I FOILed this, factored the 2 out, just because I noticed it at this point. Now I want to factor what's inside these parentheses. And this should be a positive 1. Now I need 2 numbers that multiply to give negative 12, add to give positive 1, 4 and negative 3. So I rewrite that x as a 4x and negative 3x. Factor an x out of here, and I left with 3x plus 4 in the parentheses. What do I have to factor out over here to get a 3x plus 4 in the parentheses? I have to factor out a negative 1. And you can see I'm right back to where I started. Another problem here. Cosine squared theta over 1 minus sine theta. We're going to multiply top and bottom by 1 plus sine theta. And we know we can do that, or we know that we should do that, because whenever you see a 1 plus sine theta or cosine theta, 1 minus sine theta or cosine theta, you know you multiply the top and bottom by the conjugate, you're going to get, 1 minus cosine squared theta or 1 minus sine squared theta. You can use the Pythagorean identities to substitute. So whenever you see something like this, it's not a bad idea to try this. Now I'm not going to multiply this. I'm just going to leave it as this. Now, how did I know that? I didn't. If I'd have multiplied that out after my next step, I'd look and go, oh, I need to factor. So I'm just not even going to multiply it in the first place. Okay, what's my next step? What should it be? Well, if you said that we could replace 1 minus sine squared theta with cosine squared theta, you were correct. And these cosine, now see, again, as I said, had I distributed that, I'd have to factor it out to divide everything by cosine. So what we have been doing here is we have been making a lot of trig substitutions into these equations. You'll find in the calculus that you will need to make a lot of trig substitutions in order to what's called integrate. You want to, for instance, find areas under curves. We'll make trig substitutions. So this is our first real drive at trig substitutions. We're trying to make things look a little simpler. So that's all I have for this video. Have a great day.